All right, very good morning. Thank you so much again. And let's begin quickly. I know there's a lot to cover. So I just have a question. If you could just let me know by raising your hands, how many of you have actually some kind of research or has come across any kind of topics that you've learned? You can just raise your hand. One certain leader. That's what I'm going to assume that it's coming to this topic. Alright. So when we just begin from the very simple start, and then just stay with me, and there will be some websites that I would like you to note down, so that it can really help you with the future of quantum computing. If you like research, if you like to do some research or run some experiments, there are some websites that you can take note of that you can actually run these websites and check out and see more. And in case of students, people have no doubts regarding quantum, especially the CSE third years who have recently attended my session. If they have any more further doubts, you can kind of guide them through the whole 1 year that's left for their term information. So I just want to start with a classical computer. A classical computer is our laptops, PCs, supercomputers, even mainframe computers. And I call them, even though I call them supercomputers and mainframe as normal classical computers, it's because of just one reason. They lack something called superposition. So in a normal system, the CPU, the way it processes information is if you have an input, which is your keyboard or your mouse, right? And then it basically assesses your input, then analyzes the input, and then processes your input, and then finally gives you results, an answer. And the answer is always 1 or 0. In a classical computer, the answer for the information is always binary and in a single form, and it's in a straight line. If you're reading a book, the information is always read from the left to the right side. 1 0 1 0 0 0 1. That's how the classical computer works. But when it comes to quantum computing, and now this is where you have to start visualizing things. Alright? So it's no longer a linear scale pattern. The way a quantum computer scales up, the power is still immense. For example, it's able to see 0.1 together at the same time. This state is called superposition. This is called quantum state, 0 and 1. This is the superpower of the quantum system. Without the 0 and 1 to be visualized at the same time, a quantum computer would be just a very fancy classical computer. It would not be to have all the coding systems, but it would be a very, very normal computer. So the superpower is in superposition. The superposition is also called or is enabled by a gate. So gates are basically functions, right? So if you see code, if you're into coding in Java or Python, you will enter a whole line of code or a series of codes, right? But in this, it's all about functions and symbols. Each symbol has a function. Okay, so I just move on quickly, and I just want to mention to you over here, like it's mentioned. So classical computers use bits, packets of information. Over here, for quantum systems, it's called qubits. That's basically called quantum bits. It's just quantum bits, it's called qubits. It's simply saying 0 and 1. But the amount of zeros and ones are a lot more than classical computers. For example, the exponential power grid. So I explained linear on a graph. A CPU or a normal PC will start off slowly, right? This is the graph. This is how it starts. And this is called linear speed up for a processing system. But when it comes to quantum computing, they have an exponential speed up. So in that graph, it is just at the top and it's right. It's going up from right from above. So imagine the max start of the graph is already at that speed from the first millisecond. So it's like riding a bike 206 gear from the first as you leave the clutch. If you're an active bus, it's like you just accelerate and you're at top speed immediately. So the difference between that and a classical computer and quantum system is that. Another way I can explain to you about the zeros and ones, how it is possible for a system to view it, and how the exponential speed up happens is, what I tell the students, a tree imagine a tree, right? A tree, the stem would be the 0 and 1. A stem would be 0 and 1, right? And then when you go up, the tree splits into branches and leaves. So imagine every branch is a 0 and 1, and every leaf is a 0 and 1. And even on the leaf, there are these small little veins. Even those are 0 and 1s. So you're seeing the way from 0 and 1, it just splits up, and exponentially the speed is just available for the quantum system to use. So that is the best visualization about a quantum system's CPU, how it works. The way it speeds up is exponential. It's just 1 and 0. So qubits are lines of information, and qubits hold a lot of zeros. So I'll just show you a few examples of how many, of first how it all works, how it all looks. So this is a website I would really like if you want to try and keep this is called IBM Composer, alright? So this is a quantum system. Alright, over here, already an experiment was done. I ran this yesterday with the students. It's called superposition. Half of the zeros and half of the ones, seeing 0 and 1 at the same time. These are your symbols. These are your symbols. So there's a quantum company, it's an IBM's quantum kissing or quasar. This is what basically is used even in Dell, but not extensively because it's a proprietary software. Every quantum chip has its own software. So for medical research, you have your own quantum software. For medical science, it has its own quantum software. For stock market, it has its own quantum software. So every quantum chip has its own software. This is just to run simple experiments. That is possible only on a classical computer, because if our system will start failing once we cross many qubits. So these symbols have functions. This is called the block sphere. The quantum system is looking at this. Now over here, you can only see like 1 0 over here, right? And it's a get value, it's a get 0 that you can see. I just will get back to the theory part, and then I'll just show you practically later on how this works. I just wanted to show you first how this looks, a quantum UI, how it looks, and what a block sphere is, and how the symbols and the code is when this is being entered. You enter your code here. It's quantum code, it's not Python, it's not Java, it's quantum code. You can get that in Gemini as well. You can ask Gemini. I use AI a lot, so if you want in this specific problem and a solution, you can ask Gemini to give you a code that runs on IBM's digital quasar, and enter it over there, and it will show you on the graph and on the block sphere how it is visualized. So it's just a visualization simulator. This is a simulator. It's not a real thing, but it's about 95% the closest real-world usage to a quantum system. Okay, it's called IBM's Composer. If you type in IBM Composer and the first link, Composer, you will come over here. Again, this is not a free website, so you only have 10 minutes of running free, experiments. After 10 minutes, basically, you have to make a new email ID and use it in 10 minutes. Make a new email ID, sign in, and you can use 10 minutes extra. So this is the paid service. And this is quasar. So right over here, if you want to switch to Qiskit, it's right over here. You can see Qiskit is right over here. It just changes the code language. That's about it. So for beginners, people who are just new into it, I don't always say open quasar is better understanding of you. And also use perplexity, another way you actually learn a lot more faster. So there's another way as well. I even showed this, an example of quantum circuits, right? So this is a class of quantum circuits. These are all the formulas available at the bottom, and at the top they have these functions. The whole UI is a bit different, it's two-dimensional, but the idea is the same. These have functions, they rotate the block sphere. Your block spheres are over here, and each line over here is a qubit. This is a qubit, sir. I just want to make sure, like, each line is a qubit. So one line will hold 0, 1. That's two numbers. time we'll hold 4 numbers. Third time we'll hold 8 numbers. After 8, 16, 36. And by the time you're at 10 numbers, you're over 100,000 numbers. At least 10 lines, 10 lines of qubits, you are at 100,000 zeros and ones. So I will show you on the IBM's UI of how you can see those 1,000 numbers on the surface of the block sphere. Just keep in mind, the numbers do not exist inside the sphere. They are always outside the sphere, on the surface of the sphere. Because if it's inside the sphere, it will cause density or data, and then that will cause more distance. So everything is on the sphere's exterior. So let me just go back to my, quickly go back to my, yeah. So we will look at the first thing, right? So my BPD. So these are the 4 fundamentals of quantum computing. Okay? And superposition. You can see over here, qubits can exist in multiple states. We will talk about states. I will even show you this. You can even take a photo of every slide I show, just for the reference as well. So qubits are existing in multiple states of 0 and 1 at the same time. This is the superpower of quantum systems. Next is entanglement. Till date, now this is a very interesting topic. Why? Because in today, even in colleges and universities like Stanford, Harvard, they still have huge debates for this very topic. One word, entanglement. Entanglement is an unrealized correlation between the zeros and ones, or 2 entities in physics. And this is why this is such a huge topic, even till date, is because even Mr. Albert Einstein, a great scientist, was unable to explain how entanglement works. He was unable to explain. And then his opposition was Mr. Neil Bohr, and he was not a scientist as well. So Einstein likes to have everything on paper. He likes to have a complete, a formulated whole explanation of the theory as well. But when it came to entanglement, he was not able to explain how it works. A simple example of how I can explain this, I'll give you 2 or 3 examples of how entanglement works. First, the basic logic. Twins, if you know twin children, will look the same, and then if one is in London and one is in, let's say, the USA, and one twin bursts into while walking, the other twin kind of feels the pain, right? They have that unexplained connection. Or if you're having a bad time, your parent just simply calls you and says, "What's wrong?" And you didn't even tell them something is wrong. But your mom or your father says, "I know you're my child. I know what's wrong." Even without informing them. Or even there's another theory where you can, Schrodinger's cat. It's a very old, 100-year-old theory of a cat in a box with poison gas and a light particle. So as long as light particle is active, the cat survives. But only when you open it, you will see the cat is alive or dead. So measurement will come into measurement, which is the last part, observing. So quantum systems basically view zeros and ones. It can view a billion numbers. Okay? It can view a billion numbers. And it can give you the answer, it can know the answers. So the quantum system will know the answer before measurement. Measurement is for us to understand. It brings down all of that formulation and all of that computing to a single definite classical answer, which is classical computing. So classical computing answer of 0 or 1 for us to understand. So this is, and obviously I just showed you what the block sphere is. We'll get more into the block sphere as we know more. So these are the main fundamentals of quantum computing. Without these fundamentals, everything collapses, nothing works. So at least the 0 to 1s at a glance, you can see all of them. Entanglement, you're able to map, plus it also gives a spinner. So entanglement is on that block sphere where the quantum system is viewing many, many zeros and ones, right? Entanglement works in a way where the quantum system is not opening every 0 and 1 to check. It is predicting. So quantum systems are very good predictions. Also, a fun fact, quantum systems also make mistakes. They have a habit. It's a habit that quantum systems have, that they can make mistakes because the power, the density of data, the measurement part of it, the decoherence which we get to, the disturbances that happen are at such a massive scale and just so delicate that usually you would run an experiment at least 2 or 3 times, and then from that you would get an average value. So every scientist who runs a quantum system, when I send them a good demo, I have to run that demo at least 2 or 3 times so that I can get the average out of that industry's problem and then give them a specific answer. So it's always quantum calculations even after the experiment. And this is like a habit, it happens. There are ways that, and remedies that kind of work against it. And I will explain to you about conjugate transports and all of it. But if you can just take a little bit more time, we will have this explain a little bit more. So this is the block sphere that I showed you over there. X, Y, and Z. Most of the ones are available at the top, and the zeros are available at the bottom. And these lines are simply those flat lines on the qubit. So each line is a qubit. Qubit 1, qubit 2, qubit 3, qubit 4. And most of the equating or the computing power happens at the middle of the sphere, at the equator of the sphere. So most of the computing power, the numbers keep coming down and they compute over here. As you can see, since there's less space over here, so you will see less numbers, zeros on top, and then ones accordingly, respectively. So x, y, z is just not x, y, z. This poly x, poly y, and poly z. They each have functions. They rotate the sphere clockwise, anti-clockwise, or even horizontally as well, and vertically as well. They move the sphere for the quantum system to see the zeros and ones available. So I'll just show you quickly how the zeros and ones are added on the I-waves quasar, so that you can understand how it works. And I'll also show you measurement as well quickly, so that you can see how it collapses the zeros and ones. I think I will be power cable. So sorry about that. So actually I need a power cable. Power cable. Power cable. So sorry about that. No, it's just power cable. So yes, I just want to also mention before I get off this slide, this is how the zeros and ones are displayed in a quantum system. This is not just zero. This is called ket 0, and that would be called ket 1. So the symbol is a column and a 0 and a half bracket. So ket is how we pronounce the zeros and ones in quantum systems. Alright. So I'll just go to IBM's website again, and I'll just show you how basically we can add. Right. So I just want to show you about before I even go to the next part. Right. So this is just an idea of the numbers that how exponential speed up happens, how the quantum system is able to get so much of data with just a little bit of qubits. Alright. So over here, like I said, one has one qubit line, the line I just showed you, has two numbers, 0 and 1. Then it has second part plus 4. And as you come down, right, as you come down, so as you come down, you can see over here 10, just 10 cubic lines, like 10 cubic lines. And just keep in mind, you can add 1,000 cubic lines, okay, 1,000. The quantum system, the way it works, you can add 1,000 cubic lines. So over here you can see at 10, just at 10, you have 1,000 numbers over here, right? Just at 10 cubic lines. And then when you scroll down a bit more, at 20, just 20 cubits. So you will just have 10,000 numbers, right? So imagine the tree right now, right? And then zeros and ones. And this is what basically is exponential speed of the quantum system. Just 10 more qubits you add to it, 10 more lines. And you're at a billion numbers. Billion. So at 20 qubits, you're already seeing a million zeros and ones on that block sphere. Okay, on that block sphere, you're able to see 0, 1, 0, 1, 0, 1. At just 20. Now, a billion seconds is about, I think, 12 days. Okay, a billion seconds is about 12 days. So just keeping in mind that when I go down to about just 30, now from 10, you're 1,000, at 20, you're at a billion, and now at 30, we are at a billion numbers. A billion seconds is 32 years. A million seconds is 12 days. So the difference, the exponential amount of power that it has, the way it scales up itself and becomes a quantum system, is just unimaginable. Because at 30 qubits, and I said, like at 30 you see a billion numbers. We cannot even write a billion numbers. It would take us a long time to do that. And I said, we can add 1,000 qubits. So you can see 100 to the power of 100 to the power of 100 to the power of 100. So you can see quadrillion, billion, trillion numbers at a glance. And this computing happens in a few milliseconds, maybe 4 or 5 seconds. So quantum systems again are expensive to run because they run on super condensed cooling systems which have to be absolutely, you can hear this AC, right? It makes some sound. So a quantum system has to have cooling of minus 270 degrees. The quantum chip is, okay, so it's 15 millikelvins. It has to be cooled down to minus 270 degrees with a cooling system that does not make noise or vibrates. A vibration, again, the system is very delicate. So even a vibration for a quantum system can give wrong results, fatally wrong results. So it needs a very high-tech cooling system that's absolutely quiet and cools the quantum chip in pulses, because you can't put this liquid nitrogen on the chip and immediately it's frozen. It will even break the chip. It's also very, very delicate as well. So this is how complex the quantum system is. So what's happening in Amaravati as well, we are installing something like that. When you were walking past the office, you would never know that quantum simulation is happening because it's so silent. Only outside you would see a whole room, such a big, huge chamber of air coming in and then getting cooled and then getting sent down to the quantum chip. So plus, after quantum chip, it does, since it's dealing with a billion, trillion, quadrillion numbers, it gives out heat. It gives out massive amounts of heat as well. So to maintain that temperature of the quantum chip and not basically fuse, it has that cooling. As well, the electricity that's used, you need a power plant to about 10 megawatts to get your quantum chip to run. There are sizes of quantum chips. There are small, tiny quantum chips, and there are huge quantum chips that are used for mega companies. They are doing, let's say cosmic calculations, outer space calculations, calculating stars, their density, their power, all of that stuff. So it depends on the chip size as well. So moving on, I'll just show you about this. Right. So on this, if you can guide the students as well, if they have questions, just move. Okay. So this is a qubit. Alright, this is a control qubit, control non qubit. So you add cubic lines over here. This is how you add cubic lines. This is very easy, add cubic lines. And you see, our normal PCs, after maybe, you can see, right? Every time I'm adding a line, there are lines formed on the block sphere as well. So you can add 1,000 lines if my system would handle it, or add 1,000 lines. But this is how it works. Alright? And see, over here, by the sixth line, I'm getting an error, like, my system is like, hey, this is as max as you can go. Because the computing power is not that much. You cannot handle it. So this is what the physical constraints of RAM and all of our normal classical computers suffer from. They can't go to quantum state. And to reach a quantum state also, it has to reach minus 270 degrees. Only then quantum behavior is observed. Other than before 270 degrees, it is not a quantum system. It is just a regular CPU. So physics also plays a big part in quantum chips. Alright. So quantum mechanics, all of it comes into picture only after minus 270 degrees. This is how the quantum chip really comes into its quantum state. Alright. So I'll just add, this is the H gate. H gate is called the Hadamard gate, or this is the gate that creates superposition, zeros and ones. Okay. So I'm just going to go ahead and add these gates, and then this is, as you can see, whenever I hover anything, right, hover my mouse on these symbols, they have like something written on them. They're the name of the gate. These are the gates. That's the name of the gate. So this is a controller gate. This is a reset gate. This is a mesh gate, and this is the hardware gate. That's the main gate, the most important gate in quantum systems. So we add it. And let's have a look at the block sphere over here. So I've successfully added about just six qubits. Just six. This is not a lot of numbers in quantum reality, right? I've just added six. This is the block sphere. And if you see carefully, all of the zeros and ones, you can see over here, right? 0, 1, 0, 0, 1, 1. Everything is on the surface of the block sphere. It will never be inside. So I can just rotate the block sphere as well, and you can look. That all the data is visualized. And these lines basically inside the block sphere is mapping every 0 and 1. So even if there are every trillion or trillion numbers as well, each number can be tracked individually, either 0 or 1, no matter how many numbers. So the way I work in Dell is, this is just one block sphere. I usually have about 20, 30, 40 block spheres with about easily crossing 100 qubits, and then there's a whole menu. So there's, like, this is just one UI. There are many UIs for quantum computing. So this is just one of the UIs. And when I'm running them, after setting up everything, it's like putting your chessboard ready, and then only then I click the start or run button. So the setup and run button would be right over here. Just to know, when you add your code over here, the setup and run is over here. This is if you want to get some experiments done, this is how you set up and run. Alright, so now I'm going to show you. Now you see the 1,000, or let's say you see about maybe you see about, roughly about 1,000 numbers you see over here. This is 1,000 numbers. So now I will show you measurement. We measure to understand what the result is. I will keep adding measurement gates to every qubit line, and you will start seeing these numbers collapsing. And they collapse not because of a problem, they collapse for us to understand if the answer is 0 or 1 in binary form of computer language. Right? So I'll just add this measurement gates in this show. As I have the measurement gate, you will just start seeing the numbers to that. So you can see with just 2 or 3 measurement weights, half of the data is just kind of collapsed. It's not gone because the head states are still very much active there. So the algorithm superpositional state is all available, but we are just measuring it for our understanding. So this is how a quantum system works, maths. So I'll just continue adding until we get one single answer. As you can see, after adding, the solution is still there. These thousands of numbers are still on the block scale. Alright? To add a measurement is to get the final answer. If you can get the answer on different types of UIs, right? You can get it on a system or on a graph, or you can see as a graph it's showing here. It shows you the answer of 1 or 0 mainly. And over here, if you click, it will also show you the probability of how the 0 and 1 even came. The probability of it should have been 0 or should have been 1. Probability, predictions. This is what quantum systems usually do. So when you see these 1,000 numbers, right, entanglement, the way entanglement works is now the system is not going to go to every 0 and 1. So I'll just delete a few of them so you can go back. Alright, so we're back over here. All our numbers. So, what happens in entanglement? Now, superposition is a superpower. Entanglement is the computing algorithms exponential speed up part. So, what is the quantum system doing? These fundamentals, or this entanglement that is basically unexplained. This is correlation. So every 0, even if a 0 is over here and the next 1 is over here, they are always correlated. Now, what an entanglement does is the quantum system is no longer going to see every 0 and 1. It will read the first 3, first 10, first 1,000, first even 10,000 zeros and ones. After the 10,000 numbers, right, it starts to predict. For example, let's say if each 0 is a rasgulla or gulab jamun, okay, gulab jamun, right? So one over here is gulab jamun, the next box is gulab jamun, the next box is gulab jamun. This is a truck of gulab jamuns, right? So you will know as a person or as a quantum system that you don't have to open each and every box because you know that every box you open is going to be a gulab jamun, right? So you can predict that this is gulab jamun in the next box. This is like an underrated correlation. This is the underrated correlation that even Einstein kind of is like, how do I explain this? So entanglement in a quantum system basically is this going to touch and start speeding up from here. Out of 10,000 numbers, it will just start touching and speeding up the whole process and going through a billion or quadrillion amount of numbers in a few seconds, all right, in a few seconds. And just so you know, a quantum experiment. So when you run a quantum system in real time, right, for 60 seconds, just to use the system, 60 seconds is 12,000 INR for a normal chip. So for 10 minutes, it's 1,20,000. If you use the quantum system for 10 minutes, it's like 1,20,000 because of the cooling, because of the current, because of the infrastructure and the processing power. The cost of running something like this is really expensive. So if you want to run an hour's worth of experiments, you're going into crores of investment before you run something like that. So you have to be like very mindful. So when I'm giving demos to my customers, and be a medical pharma company or even a company like JP Morgan Chase, they want some new kind of tech, right? And they're the world's biggest bankers, private bankers. So they want quantum for their stock market optimization. When I'm giving them a demo, right, and I'm spending, let's say, 30 minutes, I'm going close to a crore of rupees just to give them a demo of it. And I have to show them because the people fly down to Hyderabad and they want to sit down and see how one chip really works. So I have to give them a demo. So I'm a quantum architect. We get to the part of the career pathways as well of how to get to something like this. Okay, so this is basically what your students on CAC know how to use. 20-30 of them have actually good, and I tell them, so you can run experiments for superposition, 10 kinds of superpositions, 10 kinds of entanglement, 10 times of debugging programs. If you do that, there's a whole capstone project that they can do. And it's all available for free on Gemini, even IBM certification. So there's an IBM quantum certification which is for free that you can apply for and add to your resume that brings a lot of money. Because the quantum community is very, very small. It's not big. There are many people applying for computer science jobs, Java programmers, Python programmers, web developers. There are millions of people doing that. But the quantum community is very, very small. And I'm not joking. When I say very small man answers, it is very, very small. In all of Andhra, I have not seen one quantum fellow but who's used the system. They are studying, but they have to use the system. They don't have the experience of using the system or giving a demo to a customer or selling one of these things. And each of them, each quantum chip, the starting quantum chip is about $600,000. Starting quantum basic chip, like an i3, not an i5, not an i7, not an i9. But a basic quantum chip around $600,000 with the whole infrastructure we use. So these things are really expensive as well. So yeah, I think it's already glitching. My system is like, please leave me alone. So yeah, before we go to the next part, I also want to show you that how basically the speed occurs, the speed and the amplitudes. I just want to show you that because I think go to the next one. Right. So this is Perl. This is one of these advanced 2D circuits that are free to use. This is unlimited. This you can learn, use unlimited. Also, before I go to anything, the menu. Over here you have a tutorial on how to use it for each quantum system. So there are about, you can see, I'm not sure if that's clear, but there is like about 3 to 4. This is called AL Cluster or Quark Simulator, QUIRK, Quark Simulator. Right? So it has about grower search, Shore for cryptography, grower searches for unsorted data, for anyone who's doing BSc data science, and they have let's say big data that they're working with, and they want that big data sorted, because when you work in MNCs or you work in any company, your boss tends to give you 100 Excel files with 100,000 entries, and usually they're unsorted. And we have to sit down and do the sorting of every data. So growers, the channel is one such logical system that helps you sort the data by just entering the same Excel file, for example, many times. So say you enter the same Excel file many times and add each Excel file you add shows algorithm, the formula. When you add that, it will create layers of data, and then the quadratic speedup happens. Something called a quadratic speedup. Now we know exponential, we know linear. is something called a quadratic speedup, which is basically just for sorting data. It's not very fast, but it's more about possibilities. It goes through a billion ways to give you what is number 1, 2, 3, 4, 5 from an unsorted database. So if you have 30 pages of the same Excel file, like for example, I'll give you another example as well, like how it kind of works, or how the one system goes through Excel files, right? So in the most silly manner, I'll explain, okay? Dosas, alright? Dosa, the chutney will be the formula. Now imagine one dosa, chutney, dosa, chutney, dosa, chutney. These are your Excel files. The chutney is your formula. So then you put a needle into the dosa and it touches the plate, right? It reaches the bottom of the plate. That's how it reaches the bottom, right? It kind of spots and makes its own pathway, guessing and coming down to the final part and stops. That's what reverse search algorithm does. Basically, it's layering information, layering Excel files, and then the quantum system is seeping through, moving 1 and 0 and 0 and 1, 2, 3, 4, 5, 6, and sorting many possibilities and giving you that sorted data at the end of the simulation, at the end of the experiment. It will be able to sort billions of numbers, so billions of predictions. So these are billions and trillions of numbers. This is not normal when it comes to classical systems. People who are not using these systems will have a hard time to understand what that really is. I would always encourage you to try and think as massive as possible to understand the concepts of something better. Because it starts off with PCs, right? And then you have supercomputers, and you have mainframe computers. Then you go to servers, right? Servers, Linux servers that run huge OSs, for example, or Google or whatever. And then you go to cloud computing. Cloud, because everyone uses Google Cloud, or they have even cloud or even quantum as well. There's even cloud computing for quantum as well. But above cloud computing, the final frontier is quantum. That's the final frontier. There's nothing more above quantum. Like you're able to measure atomic values with quantum systems. You can't do that on a classical system. So you would have experiments with quantum systems. So I will move on. So I just want to show you one last thing as well. So these are amplitudes. This is your block sphere. This is your on and off switch. I'll just take about 10 minutes more. Yeah, I'm sorry, 10 minutes more, and let's move on. So I just want to explain to you the speed part of it, right? The speed up part of it. So right now, the computer is locked to the end of there. It's just reading 4 or 5 qubits, right? So the moment now I'll show you what the quantum system does, and keep a track of even this set, the amplitudes, right? Okay? So when I'm going through more and more of this qubits, because there is more data, you start seeing a pattern that is all moving faster and faster and faster and faster and faster. Why? Because more amount of data is like more amount of engine oil in the engine, and it moves more faster, more smoothly. The way it works is it runs best when there is more data. The more data, the more faster. The speed up, the exponential speed up logic comes from here. The more amount of qubits that you have, the more amount of speed that you can gain. So this is how it works. So I'll just quickly go to the final part of our website, career path, okay, and also a few things of the future that you can take pictures of. So this is the entanglement part. These are polygons and gates that have functions that each x, y, and z rotates the block sphere accordingly. To see all the zeros and ones, you would use these gates, poly x, poly y, poly z, and had one gate, which is the most important gate. So if you want, I can share the PPT with you so that you can have it as reference for all the servers and maps, and that will make it easy for you to just go through one side form here. So, yeah, we just seen collapsing. We also spoke about collapsing. Right? Collapsing is measuring. So whenever you measure something, the zeros and ones get collapsed to a final definite single definite answer, 0 or 1. So research algorithm, cryptography, for cybersecurity, and quantum programming. This is Qiskit and IBM's Qiskit, and then serves Google. Serves Google is unfortunately a paid service. It's quantum. Basically, the hello world or is saying hi in the quantum world would be this. It's very different than quantum code, as you can see. It's not like Python or Java. It uses different words. So, cloud simulators. Yes, this is basically what you should focus on. If you are learning, so I told you, right? I showed you the IBM's model. So 10 of single qubit operations, 10 of creating entanglement, 10 of implementing algorithms, 10 experiments. You can actually ask Gemini to give me 10 of each program with problems and solutions. Run them on the IBM's Qiskit and actually get proper visualizations of how to run quantum simulations. In the future, if you do apply for that job and try to get the job on a cover thing. So yes. So debugging technique is the final boss. By the way, if you know how to debug a quantum program, basically reverse, go back in time and fix a quantum code. If there's an error, that is your final boss. That is where you are the senior in the quantum. You know how to fix quantum code. That is the final boss of it. So, yeah. The future. So for the last 30 years, we've been using superconducting chips. This is what Einstein, Niels Bohr, Paul Dirac, all these scientists that have created this system. We have been refining this system for the past 35 years. Right now, we're using trapped ions, basically light particles and lasers, and in these light particles, which are so tiny, there are zeros and ones. We are able to manipulate light, enter data in it, and even reset that data for a future use. This is the future of photonic systems. They plan to use a quantum chip in room temperature. So you do not need to freeze it to -270 degrees. You can run a quantum chip in room temperature. This is the next future. So IonQ is one of these companies that are making these chips and trying to make it possible right now. And moving on. So yes, decoherence, before I let you go. So the mistakes that happen is because of few things, which is the vibrations of even the land. So for example, if one system is working, and then if a truck just goes by, right, these big trucks, the ground kind of shakes, right? When you see these big trucks just going, the ground kind of shakes. Even these small waves also create disturbance. So the quantum, the building, even the quantum computer itself has shock absorbers that do not move the quantum chip while it's processing, even for a millisecond. It will not let the vibrations be available. Also, even if sunlight comes on the quantum chip, it kind of explodes, cosmic rays, infrared. It has to be done in a vacuum. All of this also, apart from cooling and getting the electricity and handling that heat, everything works in a vacuum. So there's no oxygen also around when these systems are functioning. There is no oxygen. So if all of this is there, then decoherence, which is the enemy of quantum, doesn't happen. Coherence is what you want. Decoherence is the enemy. It's like why mistakes happen in quantum systems. So moving on, there is something called over here. To fix this, people create a path to fault tolerant quantum computing. They create codes or they use symbols, these functions. It's called conjugate transpose or a dagger. Basically, they use a dagger symbol to go back in time to fix codes. And the system is called path to fault tolerant quantum computing. So these systems basically stop decoherence. They stop the mistakes. This is the solution right now that we have. So these are the main industries that are actually using quantum systems as of today. These are the 6 main industries. So if you like medical field and what is going to create chemicals or create also medicines. Next you can go medical science, management marketing, cryptography, that's your stock market, and machine learning and optimization. So AI/ML also has a very big scope in this. Into the future. The future of quantum computing is artificial intelligence, machine learning, and quantum computing all together in one. That is going to create true AI. So that's what they want to do right now in the world. And you can see there are many examples, but let me just go to the last part over here. Yeah. So this is what very few career paths. Well, your designations that you get in the quantum world. So I'm an account manager, but also a quantum solutions architect because I sell these systems to companies that require it. Yeah. No, anything about it. Just a minute, last of it. We can take a photo of this quantum solutions architect, quantum educator, a research scientist, and quantum hardware engineer, quantum software developer. These are your actual real world designations that you will achieve if you are in the quantum world. This is what they know you as. This is your designation, what you call it as. So that's about it from my side. Thank you so much, sirs and ma'ams, for sitting through this 1 hour. I really appreciate it.
Thank you so much, sir. Actually, we have many questions, but actually the next resource person is waiting in the office. Maybe we have to call them. So afternoon, sir will be available. If at all anyone is having any questions, we'll have an interactive session in the afternoon. Okay, please note down your questions. Thank you, sir, for coming here all the way. Sir, I request the academics, sir, please honor and Vishnath, sir, and any other co-hosts or exec members, please come on to the dais. Sir, Padmanus, please.
Thank you so much.
1 second. Smile. Okay, ma'am.